Okay, so now we're going to talk about how you can calculate an ANOVA. And the question that I've used is question number 6 in chapter 9 of the book, which starts at the bottom of page 202 and ends over on page 203. I've copied the data right here for you. And remember that an ANOVA is intended to help us evaluate whether there's a difference among the means of 3 or more groups or samples. And remember, we also talked about the fact that it's a little bit of a mislabel because ANOVA means analysis, AN, of O, variance, VA. But you really, even though you're analyzing variance, the purpose is to establish whether there are differences among means. Now, in general, the way the calculation works for an ANOVA is this. You're trying to figure out how much variation occurs across groups versus within them. And the bigger the across factor versus within, the more likely you have differences among means. Now, here is question number 6 asks, is there a difference in the yield in wafer cleansing steps? So we're looking at integrated circuits and are manufactured on silicone wafers through a process that involves a series of steps. And that is cleansing steps. So we're seeing 3 methods, and we're trying to see if there's a better yield in one of them versus the others. Now, what I did immediately is I took an average here of each one of them so we could get the group means just to see what they actually look like. And you can see, just even by looking at them, these two really don't look all that different, to be sure, just on glance. And this one, maybe, but not that much. So, even looking at them, just at the data, it seems like there may not be enough difference here. But that's why we actually subject it to scientific testing so that we can figure it out. So first what you would do is, in terms of doing an ANOVA, is getting the grand mean, which is an average of all the data points. So here, if I plug that in and then look up at my calculation, I took the average of A7 all the way through C12. So go from here down to here, and that gives me the average of all of them, which is 31.333. Okay, then what you would look at next is the sum of the squares for the whole data set. Okay, so essentially we're looking at variance here. And so what you would do is take each data point, each one from each cleansing step, and subtract it from the grand mean. Okay, so 38 minus 31.33 equals 6.667, and then you square that, you times it by itself, and you get 44. You'd then take number 34 and subtract it from 31.333. You get 2.667, and square it. So there's 34. 38 minus 31, etc., all the way down to 30, which is down here. 30 minus the grand mean equals negative 1.333 times itself, and then you total them. You get 588 in terms of variation from the big mean. Okay, so you get that. Then you get the sum of squares within the groups. So this calculation is trying to look at how much variation is within each one of these. Okay, each one of these. So you're going to have to do 3 calculations. You're going to do one for the new group, new 1, then new 2, and then standard. And as you might anticipate, if you're trying to figure out the variation within one group, you're going to subtract each data point from its group mean. Okay, so variation within groups. So when you think about it, if there's a lot of variation within the group, and we've literally just looked across the groups here, just at the actual means, it's questionable. And meaning if there's a lot of variation in here, but you just look and there's very little here, then you think, oh, I may not get a positive test. There just may not be enough evidence. Okay, so for new 1, as you see, the average is 31.88. So you take each of the data points and subtract them individually from 31.833, and then you square each one. So 38 minus 31.833 equals 6.1667. You multiply it by itself, and you have the sum of the squares for that one. Go through all of them, you sum them, and then you get 264 in that case, the sum of squares for the new group. Then you would go through with the second group. Its mean is 31.66, and here are all the data points individually. So you would copy and paste those here and go through it. 29 minus 31.66, which is right here, equals negative 26666, times it by itself. You get 7.11. You sum them, and you get the sum for that group. We would do the same thing for the standard group, and then we need to get a total calculation, which is the total amount of variation that exists within group. So you'd add this, this, and this. Excuse me, not that. Yeah, just in blue. 1, 2, 3, and you get 588. Now notice 581. Notice that we did the sum of squares for the total data is 588, and we've established that the within group variation is 581. Now, really, even though we're going to calculate it by default, what this would mean is that the variation across groups is 588 minus 581, which is 6. And in terms of comparing variation within group at 581 versus across group, or we'll put it up here just to show, because we technically, I guess either way, you could go across mean, is only 6. That seems like a lot of variation within versus across, but we'll continue to go. I just want you to recognize the intuitiveness of this. Now you get the sum of the squares among the groups, okay, across them. So now you have to consider 3 mini equations by comparing the means for each group to the grand mean. So here you've got the grand mean, which we already established, 31.333. Oh, excuse me. Sorry about that. Let's see. This is the group mean. Okay. So, and I tacked this on a little bit differently, but minus grand mean. Okay. So here is the mean for each group, which we have up here, these 3. And we're looking at how they compare to the grand mean. So for group 1, you subtract 31.833 minus 31.333. You get 0.5003 and multiply it first times itself, and then you multiply it by the number of data points in each set. So times 6. There were 6 data points in each set. So you can see 1, 2, 3, 4, 5, 6. And then you get 1.50, and you do the same thing for all 3. You add them together, and notice that the total of the sum of squares within groups plus the sum of the squares across groups equals the total sum of the squares. So if you added 581.666 plus 6.33, you get 587.9989, which really would equal 588 if we just round up 0.01. Okay, now you're getting serious. You've got all the backbones of all that you need. So now you are looking at let me pull this up here. Okay, remember that the big statistic in an ANOVA is the F statistic. And what you're looking at, so whenever you get an outcome, you're going to see the F statistic. So what you're looking at here is the MSA, and the MSA means the mean square among groups, which is equal to the sum of the squares among the groups divided by the number of groups minus 1. So in this case, it's the sum of the squares across the groups, which is this, divided by the number of groups, which we know is 3, minus 1. So it's 6.33 divided by 2. There's our mean square among the groups. Then we're looking at MSW, the mean square within groups, which is the sum of the squares within groups, which we got as 581. And note again, there was a lot of variation within groups versus across. That is, 581 is substantially greater than 6.33, so keep that in mind. You divide 581 by the sample size, which we know is 18, minus the number of groups, which is 3. And so you take 581 divided by 15, and you get 38.777. Now you're ready to calculate the big statistic. The F statistic is simply the MSA divided by the MSW. 3.165 divided by 38.777, which is 0.08 as an F. Now, the critical value for this question is 3.68, which I'll just mention in a minute. And the p-value for this particular number, because remember, each statistic that pops out corresponds with p-value. The p-value for this test is 0.922, which means there's a 92% chance of a type 1 error. That means if you reject the null hypothesis, there's a 92% chance that you will have rejected the null hypothesis when it's actually true, when there's not enough evidence to reject it. So the clear outcome here is don't reject the null. Based on what we saw up here and just looking at things, there's not even close to ample evidence that there are differences across the means because much more variation happens within them. Now, the critical value, which is again another way to, you have two alternatives in any statistic in terms of how you evaluate whether to reject the null. You can either use your p-value, which frankly is plenty, and most papers never publish anything but the p-value. But from a statistical standpoint, the other alternative is to look at the critical value. And the critical value here is found under page 322. I was pointing out in other videos that there are tables in the back of your book that show you how to figure out the critical value for any particular test. So it is it's on page 322 in your book. I'll even go to it right now. And you can see it's table C.4, critical values of F. And it's under number 2, which is the numerator degrees of freedom, which is 3 groups minus 1, so that's a 2, and 15, the denominator, which is, so 2 and go down 15, and that is 18 groups, 18 data points minus 3 groups, which is 15 degrees of freedom. So you can see your number is 3.68. Now, noticing the actual statistic itself, it would have to be bigger than 3.688 to suggest that there would be variation among the means, and there's not even close to that. So just one last reminder, as an alternative to this, I think it's a very good thing to intuitively understand how the ANOVA works. However, I would rarely ever even consider having done this in practice. I would simply run an ANOVA analysis in Excel. So I think, if you understand this conceptually, and you might want to try another problem in the book to see if you can get it right by hand, once you do that and you see that the big issue is you're looking at how much variation there is across, that is the A, versus the variation within the group. So the MSA, that is the mean squares across groups, would have to be fairly large compared to the MSW, that is the variation within groups, to get a number large enough to get to this. So, as one last example, because we had a number here, 581, as within, we would have to have a number that's 3 times that size, or 4 to get to 3.68 as a statistic. I wish you well.